Welcome back to ECE 442-542. I'm very nervous because last lecture it didn't record well. The audio was terrible. So if you're looking for where's lecture 7.2A or 7.2, you won't find it. It's actually 7.2B. That's to remind me how upset I was that I had to go back upstairs and re-record the lecture. But all of the jokes, who knows what's included in that new lecture. I don't think there were very many jokes, which maybe is a good thing, during the re-recorded version of the previous lecture. So if you're wanting to know what's going on with that lecture material, because the writing may look different than what you saw during class if you were in class. Hopefully that won't happen this time. That's the disclaimer. That's the commercial. Some more commercials. Homework 7 is due on Saturday, so don't forget to do that. That's required. Project for 542 students, that's due a week from today. A week from today is the last day of class. We will have class. We will have class on Monday. I will be okay if you're not here. I'm going to try to record it so that you can watch it if you want to. Teacher course evaluations, I do appreciate you filling those out. Those help me improve the class and give me feedback on what was working and what needs to be improved. You have until the last day of class to complete those, and stay tuned. Maybe there will be some extra credit associated with that. I guess I'm feeling generous at the end of the semester. There is extra credit on homework number 8. That's due on the reading day, which is the day after the last day of class. That's why it's extra credit, but that content will be on the final exam. And that content is what we will be talking about today, which is Statespace Controller Design. That's homework number 8. The final exam is on Thursday, the 11th, and it's at 1 to 3 p.m. It will be in this room, but it is a 1 o'clock to 3 p.m. final exam on the last day of finals. One more change in announcements is typically office hours on Wednesday are from 12:30 to 2:30. Next Wednesday, I can't make that time slot, so I've shifted the 2 hours down. I've slid them down, and they will be then from 9 a.m. to 11 a.m. And stay tuned, maybe Monday or Wednesday, I will put together maybe some more office hours between the last day of class and the final exam. So I'm not sure what they will be office hours wise, but it will probably be at least what they are presently during the semester, the office hours. Just in case you want to text during the last half or the last week of class, I thought I would put some more acronyms in. We'll be talking about CTSS and DTSS. That's just the back 2 are state space, and the front 2 are continuous time and discrete time. If you see those, that's what I'm meaning. Instead of writing all of that out, it will just be continuous time state space or discrete time state space. The table of contents, which now is the goals for today, may be more than what we will cover today, but this basically tells us really where we're headed for the remainder of the semester, which is really just 3 more times that we will meet or have lecture periods. Maybe we won't meet, but we will have lecture periods on today, Monday, and Wednesday. Some of this, well, I'll get there. So we're doing state space design from today forward in this class, and we'll concentrate first on full state feedback and what that means. That now means something different than what we've been doing. Before, we've been measuring the output, and that's just been one signal and feeding that back. Now what we're doing with full state feedback, if we had a 5-state system, 5 different states, we're assuming we have access to all 5 of those state variables, and we can scale those up and feed those back to form our input. That's what we mean by full state feedback. And in the discrete time system representation, We've actually already covered some of this state space material, and I'm just reminding us where that's been. For example, converting a continuous time state space to a discrete time state space, that was back in February. If you want to go and see how do I get from an x prime or an x dot equal ax plus bu into the difference, or yes, the discrete time state space, that's back in lecture 4.3. And in fact, that was done 3 years ago. So that was sort of an additional lecture provided at that time, and it's probably not the standard 75 minutes, but it goes through that process of how do you get from a continuous time to a discrete time in the state space setting. That's in the Unit 4 material. We've talked about this summary square of zero order hold equivalence. How do we move around? How do we dance relative to continuous time systems in the state space or time domain, in the frequency domain or transfer function case, and put those into discrete time. We have 4 different locations. That's our square. And that was talked about also in February and in lecture 4.4. To get us thinking about state space, we're going to go a different direction in that square. And now today what we will cover is, starting with a transfer function, a g of z, how do we extract or create a state space representation? How do we find a phi matrix and a gamma matrix if we're given a transfer function? That's what we will do today, and that's this TF to SS, transfer function to state space. Once we have a state space representation, then we will be able to talk about state feedback, where now it looks similar. It's u is equal to minus kx, but now it's x and not y. X now is this full state vector, which means k can be a matrix. It's not necessarily a scalar. If we had one state variable, if we had a first order system, then k would be and we had a one input system, k would be a scalar. It would be a 1-by-1 matrix. If we have 3 states, an x sub 1, an x sub 2, and an x sub 3, and one input, k is now this row vector. It's 1 by 3. It has 1 row and it has 3 entries. But k in general is a matrix. We'll talk about general discrete time state space block diagrams, and then a process for designing that k. How do we find the variables, these unknown coefficients in the matrix k? And if we had a 1-by-3 matrix, then we would have 3 unknown variables that we're trying to solve for. And those 3 unknown variables in this matrix k are being selected so as to give us eigenvalues or poles of our system that we want to have. And that's why we've spent a lot of time on performance specifications. Where do we want to put these poles? Why do they want to be at 0.8 plus and minus j.2? And maybe 3 more at the origin. If that's our desired set of poles, how do we achieve that with this choice of matrix k that we're using in our full state feedback? The second set of topics deal with issues. What are some possible issues that might occur when we're dealing with full state feedback? First, we are assuming that the full state vector is available, which means we can measure all 4 of those state variables. We can scale each of those individually and then combine those up and feed them back to form this full state feedback. We'll talk about a concept of controllability, which really means you give me a phi, you give me a gamma, and we can determine, can we actually place all of the poles arbitrarily where we want? If our system is controllable, then that's possible. And we'll give a strategy for determining, given a phi matrix, the system matrix, and the input matrix gamma, what do we have to build and check to see if our system is controllable. If it's controllable, then we can find a full state feedback gain matrix K that will place our poles where we want them. arbitrarily, and we want to do that more than just arbitrarily. We have particular locations we want those poles to be, or where we want them. We'll talk about regulator design, which really means just feeding back the state and having our closed loop poles assigned. The other case is if we want to inject a reference input. Then we will have one more gain to worry about, which is the gain from our reference input into our system. And we can now use that to adjust the DC gain. And where do we like to typically have our DC gain valued when we're going from the reference input to the output? What's our typical choice for a DC gain in the transfer function between the reference and the output Y? Final exam question. What DC gain do we want for capital T sub C of Z? Typically. Pardon? Yes, we want 1. But we can disguise 1 to say 0 dB, but we want 1 if we do it in absolute. If we do it in dB, then we want it to be 0 dB. But I'm glad you didn't say 3, okay? So we want it to be 1. The DC gain typically to be 1, and that's how we will select this unknown gain value associated with the reference input. The problem with that is that that choice of gain is very sensitive to our parameters that we're assuming we know of the system, and we may not know those parameters very well. Which is why maybe the next topic might be integral control. We like to put integrators in our system, and that we could augment our system with, and we'll show that maybe a week from today in next Wednesday's lecture is the plan. Here, this should be review. This should be a review, but it's a review from February. So maybe it's still a little cloudy, but you're always in the cloud anyway now, right? Sorry. But if we have a state space control design, here's our model for a discrete time state space system. It has a phi matrix, which is dimensionally what is phi? Or what shape is phi? Is it oval? Is it oblong? Is it rectangular? It's square, isn't it? So phi is square. It has the same number of rows as it has columns. And it has to be compatible with this set of dynamic equations. Phi is our open loop system matrix. Gamma is our input matrix, which if we're dealing with a single input, gamma is going to be this column matrix, or it's going to be tall and thin. It's going to be maybe n rows tall by 1 column wide if we had 1 input. So gamma, you would be always thinking it might be this tall, thin column. And H, our output matrix, if we have 1 output for Y, what's H? Well, H now needs to somehow measure or convert the entire state vector, which let's say is, we had 10 state variables. Then H is saying, how are those combined to form 1 output? H is now 1 by 10. It's now short and wide, H is, as a output matrix. And we typically, well, correct me if I change these, but we will say that our states, the number of those are n, little n, Nevada of those. The number of inputs, we have little m or Michigan of those. I'm trying to do my geography, why did I pick a Q? But Q number for the outputs. So I don't have a state with a Q, do I? What? Yes, we could have last names now for the dimensions of our, but I don't want to call out last names on this infinitely available video. Here's a block diagram, and that's sort of a funny looking delay symbol, but I'm just trying to emphasize that that's now a bank of delays. Meaning if X is 10 state variables, I have 10 delays in that block that I'm just showing one particular block. If X is 10, what's the dimension on phi? How big is phi? What are the dimensions on phi? If X is 10, if we have 10 state variables, it's 10 by 10. So we have 100 elements in phi. I'm trying to get you ready for the final to invert these 10 by 10 matrices. Slowing you down on the final. If we have one input and we have 10 state variables, what are the dimensions on gamma? What's gamma? It's tall and thin, right? It's 10 rows by 1. What is H? This is the one I want to illustrate. It's lying down, right? It's 1 by 10 is H. I just couldn't wait to show this. This is our summary square for zero order hold equivalence. And this you already have. This is from the end of February. But we have our continuous time system representations, either time domain or frequency domain. And we have similar descriptions in the discrete time setting. But we can now go between these different blocks. We can go from continuous time state space by a sample with a zero order hold on the input to obtain a discrete time state space representation. And then we have our phi, gamma, C, and D. If we had G of S, you know how to find, and this is a good way to review for the final. If I give you a G of S, you should be able to find the zero order hold equivalent of G of S and find a G of Z. And here are the formulas to do that. What we are going to do today is actually go in the other direction. We are going to go from a discrete time transfer function, a frequency domain representation, a capital G of Z, and find a state space representation for that. We want to now find phi, gamma, oh, and now I'm labeling it something else. I was saying H, now it's C, C, and D. But that's to be consistent with our continuous time representation, which is y is equal to cx plus du. The output looks the same if we sample the time vector. If little t now becomes little n capital T. And the bottom of this square, summary square, just shows if you had A, the system matrix in continuous time, you could find phi several different ways. It's this matrix exponential, or you could find it if you went using Laplace transforms, the inverse Laplace transform of the matrix, the symbolic matrix, SI minus A inverse, evaluated at little t equal to capital T. But you've seen this before. You know how to do all of these different paths, except maybe that last path that I've indicated going from G of Z to the time domain state space representation in discrete time. And that's what I want to cover now, is what's one way if somebody gives you a transfer function, G of Z, and oh, this is talking about full state feedback. How do I do that if I have a G of Z? Well, now you know after today how to go from G of Z to the script S sub D and find the full state feedback system. So let's now start by finding, and we'll do this via an example, showing or illustrating how we can go from a transfer function to a discrete time state space. So finding the discrete time state space given a transfer function, or TF to SS. Suppose that somebody gives us the following transfer function. What could you tell me? Do you already see a root locus diagram if you wanted to design a controller for this system in the frequency domain? Do you see a root locus diagram for this system? And now I should be seeing hands coming together and then going up, right? You should be cheering in your chair. And those hands are going vertical. They're going at 90 degrees plus and minus. Was that a question or was that an illustration? That was a cheer. I forgot my pom-pom. So we'll try to, never mind. Then you would be here for sure on Monday if I said I was going to bring, never. So here's G of Z. What's our pole zero excess? You just told me basically with your arms, you now know that you have two zeros at infinity and you're going off to those in your root locus. So you have a pole zero excess of 2. What we want to do now is find a phi matrix, a gamma matrix, and an H matrix. What's the size of phi that we want or expect? What size of phi do we expect for this system? Can you tell me by just looking at G of Z? And you should know this by the final so that you can check your work. Yes, phi is like this, right? You're showing me a size, and I know that it's square, so you can, somebody showed me their fingers with some distance between, and now I had to anticipate how many rows were inside that distance, right? How many rows are inside that distance? How many rows are in phi? How many eyes do you have? 2. So how many poles do we have? 2. Well, okay. Yeah, I guess we could have more than 2 eyes. We could have 4 eyes, but anyway. But 2 eyes. 2 poles. We should have a phi matrix that's square, that's the size of the number of poles we have in the open loop transfer function, and that's 2. Not related at all to where that pole is. So don't confuse that 2 as coming from one of our poles, which is at z equal to 2. Is this system stable? Open loop? No. We have a pole at 2. Will it ever be stable with output feedback? If you just had a gain and you were controlling this with output feedback, can you stabilize this system based on your cheer? Why am I getting distracted? Where are they breaking away? Right at 1. That's supposed to be going up at 90 and down at 90. This will never be stable with output feedback. You're always outside the unit circle. Let's now find a state space representation for that, and we know that the transfer function is giving us a relationship between the z transform of the input and the z transform of the output, and they're in this ratio, the output over the input. That's now 3 over the quantity z times z minus 2, or multiplying that out, we now know that y over u in the transform setting is this ratio of 3 over z squared minus 2z. What we're trying to do is get this into a difference equation in the time domain and build a block diagram from that difference equation. To do that, we can cross multiply and find an expression, the left side containing y of z and the right side containing u of z. Or we now have z squared minus 2z times y of z is equal to 3 u of z. Again, as a review for the final, can you take this into the time domain based on this? Now you're in the frequency domain, but what's this look like in the time domain? What's a z operating on capital Y look like in the time domain? What's z as an operator? Or what's z to the minus 1? Z to the minus 1 is a unit delay. Z is a unit advance. We now have z squared times y of z. This is now going to give us y at time n plus 2. Then we have a minus 2 y of n plus 1 equaling 3 u of n. There is now our time domain difference equation that we can try to create. We want to now create an all delay block diagram, and once we have an all delay block diagram, we can label the states as the outputs of those delay blocks, and that will give us our state space representation. This is one way to build a block diagram. There's many ways to build a block diagram, but this one maybe we haven't talked about, so I'm throwing it in to give you something to think about differently. Suppose that we now have available to us or access to the input u of n and the output y of n. Assuming we have u of n and y of n, let's now build our all delay block diagram. And to do that, the first step that I'm going to do is I'm going to rewrite this difference equation by making these terms equal 0. So I'm going to put all of these terms on one side of the equal sign. Or what I'm saying is I have y of n plus 2 minus 2 y of n plus 1 minus 3 u of n is equal to 0. Have I done anything wrong? Now if somebody says, oh, you want 0? Well, if this is the system that you have, you would say, oh, give me the output at time step n plus 2, give me the output at time step n plus 1, and the input now, and I can linearly combine those in this way to generate 0. And the way I want to use that now is I want to say, oh, suppose that I have a summing junction, and that's going to be in my block diagram. If I inject 0 into that, I'm effectively injecting this combination of variables that are on the left-hand side of that equality. They're all equal to 0 if they come in that linear combination. 0 then could be interpreted as y of n plus 2 minus 2y of n plus 1 minus 3u of n. What I want to do is finally at the very right-hand side of the page end up with a combination of delay blocks and summing junctions and gains that will generate y of n. And coming in, I have 0. But what I can do is I can say, what if I have access to the input now and the output now? If that's the case, suppose that this is now u of n, and I can have that. Well, if I add 3 u of n's, what do I end up with after I combine y of n plus 2 minus 2y of n plus 1 minus 3u of n plus 3u of n? I just end up with those output terms. Well, I can do that if I take u of n now, scale it by 3, and add that into my summing junction. So that coming out of that summing junction, what do I have? Do you see that the result of this is appearing at the output of that summing junction? Inside is now y of n plus 2 minus 2y of n plus 1. If I call that, let's say, alpha 1, that's right here. Alpha 1 is right there. I have 0 plus 3u of n. I now have, coming out of that summing junction, y at time step n plus 2 minus 2y of n plus 1. I want to eventually end up with y of n on the right-hand side. If I delay that signal, with a delay, can you now tell me what alpha 2 is? If alpha 1 is y of n plus 2 minus 2y of n plus 1, alpha 2 is now a delayed version of alpha 1, or that's now y of n plus 1 minus 2y of n. And what did I say that I had access to? I said I had access to y of n. If I now take y of n and add 2 to alpha sub 2, so I'm going to take this, scale it by 2, and add it to alpha sub 2. That's what I'm doing here. What do I end up with? Just y at time n plus 1. That's now what I could call alpha sub 3, which is this signal right here. And how do I make alpha sub 3 equal y? Just delay it. Meaning now I can complete my all delay block diagram by simply introducing one more delay block, and now I have my all delay block diagram that realizes that transfer function that I had to start with, capital G of z equaling 3 over z times z minus 2. Where in this case, I have it in the time domain. If I wanted it in the frequency domain, those capital D's would be little z's. Yes? Pardon? So now, what's the question? So now I have alpha sub 3 coming into the delay block. That's y of n plus 1. I delay that. What comes out of the delay block? Y of n. So now y of n is what I've now connected on the right-hand side of that rightmost delay block. Is it making some sense as to how this block diagram, I have an input u, I wiggle that, and that will now basically solve that linear difference equation that we started with in the blue box. That difference equation is now satisfied by this block diagram. And what I'm trying to do now is find a state space representation. And the state space representation is in the time domain. And this block diagram is in the time domain. How do I find a state space representation when I'm given an all delay block diagram? What's the trick, or what's the strategy for making that happen? What do I need to do? How many state variables are you expecting to have? 2. How many delay blocks do you have? 2. That determines how many state variables you have. How many poles did we have in capital G of Z? 2. That's giving us our dynamics. We have 2 poles that influence the dynamics of this system. To find a state space representation, the trick or the strategy is to work with these delay blocks, and we label the outputs of the delays as our state variables. Let me write that down so that it's very clear. We want to label as state variables. And how I label those is really up for your preference. Meaning, a state space representation is not unique. I could label it one way, you could label it another, and it would still be modeling the same system. It might just be a different phi matrix and a gamma matrix and an H matrix, but it would still be a valid model of that particular system. For today, let me label this as x sub 1 at time n, and let me label this as x sub 2 at time n. Those are the outputs of my delay blocks. X sub 1 and x sub 2. Now I just need to use that information to allow me to write down my difference equation. If little x sub 1 of n is on the right-hand side of that rightmost delay block, what's on the input to that delay block? What's the signal that lives right there? That's x sub 1 at time step n plus 1. One time step ahead of what's coming out of that delay block. This location then is x sub 1 of n plus 1. The inputs to that are what will fill in my matrix entries in the phi matrix and the gamma matrix. Yes, that's a terrible 2. What happened to the 2? That's like a child that's a terrible 2, right? You have the terrible 2s if, never mind. Oh, and the delay block looks a little suspect, but now probably when I print it, it will have multiple lines. But I chose those variables to be my state variables because those are the outputs of my delay blocks. If I gave you on the final exam a all delay block diagram and didn't give you a state space representation, I might say, provide me with a state space representation. Your very first step would be to label the outputs of all of your delay blocks as state variables. If you had 4 delay blocks, you would now have 4 different state variables. The next strategy would be to now find equations for x sub 1 of n plus 1, x sub 2 of n plus 1, x sub 3 of n plus 1, x sub 4 of n plus 1 in terms of x1 of n, x2 of n, x3 of n, x4 of n, and u of n. We're now looking for x sub 1 of n plus 1, which if I do it over here, maybe, and then copy it down later, since it's a little bit, it'll slide off the screen. What does x sub 1 of n plus 1 equal? That's the output of that rightmost summing junction. Well, that equals all of the inputs coming in. So x sub 1 of n plus 1 is actually going to be equal to 2 x sub 1 of n plus x sub 2 of n. How do I write that in a matrix form? I first know that this is my phi matrix. And how big is the phi matrix? It's that big, right? It's a 2 by 2 matrix because we have two state variables, meaning phi is now 2 by 2. How big is the input matrix, gamma? What are its dimensions? Its dimensions have to be compatible with the number of state variables. That's how many rows we have. And it has as many columns as we have unique inputs. What are the dimensions of gamma? How many rows? 2, because it has to have the same number of rows as the state. That's what it's equal to on the left. And we only had one input, which means that we're expecting 4 elements in phi and 2 elements in gamma. And we can fill in the top row of these matrices by looking at that highlighted equation in yellow that gives us x sub 1 of n plus 1, which is 2x sub 1 of n. Where do I put that in my 2 by 2 phi matrix? In the upper left-hand corner, correct? So now I have a 2 there. Where do I put the next entry and what do I put in? I now have a 1 coefficient weighting x sub 2 of n. I said I'm filling in the top row, so I sort of gave you a hint. This should be in the 1, 2 entry of the phi matrix. And what do I have in the top row of the gamma matrix? I don't have any u directly wiggling x sub 1 of n plus 1. I have a 0. To complete the dynamic representation in the state space form, I now need to find an equation for x sub 2 of n plus 1. And I can find that by examining the block diagram. This signal right here is x sub 2 of n plus 1. And if I write that down, is this going to be way too busy if I do it right here? That's why I'm doing it there, so it'll be busy and confusing. X sub 2 of n plus 1 is equal to 0. That's the output of that leftmost summing junction, and the only non-zero signal coming in is a weighted input, which is now 3 u of n. And how do I put that into my dynamic equations? I have 0x1 of n, 0x2 of n, and I have 3 u of n. The only thing left in this state space representation is my output equation. What are the dimensions on H? Was that a dimension? I'm trying to read hand signals here, and I'm not doing a very good job of it. 1, I don't have my glasses on, and 2, those are pretty cryptic hand signals. but I'm getting dimensions with index and thumb. I'm getting h dimensions with just a point, but h is what size? Oh, h is now, nobody had their phone out, did they? Good. So you can't have any social media going during class for many reasons, and that's one, okay? What's the dimension on h? It has as many columns as you have state variables. That's the last dimension. That's the 2, and it's just one output. That's the 1. So it's 1 by 2. And the J, the direct feed-through matrix, what are its dimensions? It now needs to be compatible with one output and one input. So it needs to be a 1 by 1. It's actually a scalar matrix, but you could say, oh, that's a matrix. It's 1 by 1. What is y of n in this block diagram? What makes up y of n? Now it's too obvious, but that's the same thing as x sub 1. That's how we labeled the output of that. In general, there could be a summing junction out there, and it could have linear combinations of x1, x2, and the input. But in this case, it's simply x1 of n, and we can then complete our state space representation by filling in that information. Y of n is now just x sub 1 of n with no x sub 2 of n and no u of n. And what have we done if you are texting? We've done TF to SS. We did transfer function. We started with a G of Z. We found a block diagram, an all-integrator block diagram from that G of Z. Actually, we went G of Z to a difference equation. The difference equation we turned into an all-integrator block diagram. From that, we labeled the states or the outputs of our delays as state variables, and then we built up a state space representation. We went TF to SS, transfer function to state space. Right? Now what we're ready to do is feedback those states. Use full state feedback to change the dynamics. Can you see the dynamic behavior in this system in the state space representation? How do you find the dynamics of this system? And this is now an open loop system. We haven't introduced any kind of control. What provides us with the dynamic information in this representation? Something on the eigenvalues. We need to find the eigenvalues of our system matrix phi. The eigenvalues of phi are what? If you've had a linear algebra class, they're staring you right in the face. This matrix phi is actually upper triangular, and so the eigenvalues are on the diagonal. We have an eigenvalue at 0, and we have an eigenvalue at 2. Where were our open loop poles? 0 and 2. So we're consistent with what we started with. We haven't changed the system dynamics. Let's now look at this concept of full state feedback, where we are now building our input to the system, U of L, since my dimension maybe on my phi is Nevada, I'm going to change my index or my variable inside the arguments of my time domain index as little l. This is now minus k x of L. And in general, X is tall and skinny. U could be tall and skinny, and it's as tall as Michigan rows. It's m by 1. In our case, how many inputs do we have? I'm going to, one lecture I put laptops up here. Now I may put phones up here, and I might jump up and just stomp on those phones. What are the dimensions on K in general, generically? If this is the relationship, if this, don't tempt me. So if this is the relationship between the input and the state with full state feedback, what are the dimensions on K? What are the superscripts on R? And now we only have two states, Michigan and Nevada, to worry about. We also have two states in our earlier example. So that was maybe a play on words. But we have, what are the letters and how are they organized? You have K needs to be compatible with M inputs, so it has to have M rows. K is now M rows tall, and how wide is K? It's in Nevada. It's as wide as we have state variables. In our particular example, if I was really feeling generous for the final and I said, what is the dimension of R or of K in this example that we've been following about or talking about today? What's K's dimension? What are the dimensions of K? How many inputs did we have? 1. How many state variables did we have? 2. So K is 1 by 2. We have an unknown K1 and we have an unknown K sub 2. This 1 is the number of inputs, which we were calling Michigan, and this 2 was equal to the number of states. Why do we even want a K in the first place? Fill in the blank. I have a lot of laughing going on, and I have no idea what the laughter is about. I didn't think K was that funny, but you can tell me after class. Want to find K to do what? We are trying to adjust or feedback these states to change the dynamic behavior of our system. So we want to find K to change the system dynamics. If you're a visual thinker, then we could now connect that with our block diagram. Here was 3 that was weighting our input signal U. That now fed into a delay block, which fed into another summing junction and a delay block to produce the output Y. And here we fed this back with a 2 to produce our open loop dynamics. This was our difference equation. We had labeled this to be x sub 1 of n, and this was x sub 2 of n. We now have said we want to measure x1 and x2, or with full state feedback, we have access to x1 and x2. We can scale those, gain those up by k1 and k2, and use k1 and k2 scaling x1 and x2 to create our input signal U. Meaning U is now going to be a linear combination of x2 scaled by k sub 2, and I'll go ahead and put the minus sign in that coefficient, and it's also x sub 1 that we measure, scale by k1 and negate that, and now u, do you see that little u of L is minus k1 x sub 1 minus k sub 2 x sub 2. That's now minus kx. So does that mean there's no input to the system, is the question. Is there input to the system? Is u of L anything in this system? It's a thing. What we don't have is we don't have any external reference input yet indicated. What we will do the next time we get together is allow for an external input or reference input, and this isn't going to allow me to go left, but eventually we will have an R of L, and we'll scale that by N1 and put that in there. Pardon? Oh, why can't you see that? The projector is going crazy. So that's R of L feeding in an N sub 1, and N1 is our reference input. But today, we're not worrying about that reference input. We are, and this is what I'm calling the regulator problem, when we basically don't have an external input or an external reference. For now, then, we will, since you can't see it anyway, we'll erase that. And we'll concentrate just on having u of L equaling minus k1 x1 of n minus k sub 2 x sub 2 of n, which is minus k1 k2 or I might just say that's minus k x of n. Or you need to wake me up. I'm sleeping on that table over there. My argument was L. Okay? What we want to do now, but I hope this block diagram illustrates that now we are changing the dynamic behavior of that system. We're not just having two fed back to one summing junction. Now we have a weighting on x1 and x2 forming this new block diagram, and this new block diagram's dynamics will change based on how we select k1 and k sub 2. We want to pick k1 and k2 to give us more acceptable dynamic behavior. That's the goal. Let's look at it with equations. With state feedback, we have x of L plus 1 equaling phi x of L plus gamma u of L. With full state feedback, we want u of L to actually equal minus k x of L. That's essentially what we did in the block diagram. And what we want to do is use this u right there, or replace u of L in this dynamic equation with minus k x of L. And let's see what happens. If we do that, we now have x of L plus 1 is equal to phi x of L plus gamma times little u of L, but little u of L is now minus k x of L by design. Or that now says that we have phi x of L minus gamma k x of L, x is common to both of those terms, we can factor it out. And we now have a new system matrix relating the state now and the state one time step into the future. We've now adjusted our system dynamics with full state feedback, and we now might call this a new system matrix, capital Phi sub C, which represents our closed loop system matrix. Let's now see how we might pick capital K based on this full state feedback concept. We can return to our example, where our example now said phi sub C was equal to phi minus gamma K. Phi was this matrix 2, 1, 0, 0. Gamma was 0, 3, and K was K1, K sub 2. We okay with that? That's just using the phi matrix, the gamma, and this unknown feedback matrix, capital K. Which, if we plug all of those together, do you see that I now have I changed the top row with this feedback? The input matrix says, oh, weight the top row, these K1 and K2 with 0. So I'm not changing anything in the top row. Or maybe I should multiply that out. I have 2, 1, 0, 0. The top row is nothing. And the bottom row is a scaled version of K1 and K2. And now I can, maybe it's a little bit cleaner now to say, oh, my top row hasn't been changed by taking away that matrix, but my bottom row has changed. I now have minus 3 K1 and a minus 3 K sub 2. And now I have a different system matrix, which is my closed loop system matrix. And how do I find the dynamics of that system matrix? I find the eigenvalues of that phi sub C. If I now look, this is now my capital Phi sub C. I want to now find the eigenvalues of Phi sub C. And they will actually be, in this case, those eigenvalues are going to be in terms of these unknown gain values, K1 and K2. I'm going to have a characteristic equation or characteristic polynomial that's going to be including these unknowns K1 and K sub 2. I'm going to call that equation delta sub K of Z, and that's going to now be the determinant of Zi minus Phi sub C. Or if I use straight vertical bars to represent the determinant, Z is going to be scaling an identity matrix that has to be compatible with phi. Phi was 2 by 2, so my identity matrix is 2 by 2. Then it just has ones on the diagonal, minus my phi sub C, which was 2, 1, minus 3K1, minus 3K sub 2. Just plugging in the variables from that expression for eigenvalues. The eigenvalues of a matrix are the determinant of Zi minus Phi sub C. They're the values of Z that cause that determinant to vanish. Or we'll set all of this equal to 0. In this case, I now have a Z on the diagonal, or I could say I have Z minus 2 in the 1, 1 entry. I have minus 1 in the 1, 2 entry. I have Z times 0 minus a minus 3K in the 2, 1 entry, or just a 3K1. And I have a Z minus a minus 3k sub 2. And I now need to find the determinant of that 2 by 2 matrix, which shouldn't be that hard, right? It's the product of the diagonals minus the product of the off diagonals. And if I do that, I now have z minus 2 times z plus 3k sub 2 minus 1 times 3k sub 1. You can use your favorite technique to multiply out those two first orders. FOIL, if you learned that in 3rd grade or wherever you learned FOIL. First, outer, inner. I'm joking. You guys were laughing before, so now 3rd grade you're doing algebra, right? So now we have FOIL. We now have z squared plus minus 2 plus 3k sub 2 times z minus 6k sub 2 plus 3k1. Is my algebra okay? What I want to do now, do you see that I now have freedom to pick k1 and k2, and that freedom allows me to adjust these two coefficients in this 2nd order polynomial. And that will allow me total control over the roots of this 2nd order polynomial. I can now make those wherever I want them to be located. And in this case, what we want to do is probably locate those at desired locations in the z-plane. And those are based on circles, hearts, and angles, right? We have our settling time. Boy, we're just playing today. We've only got 2 more lectures essentially to go, right? So I'm getting a little silly. But now we have circles, hearts, and wedges for percent overshoot, settling time, not in that order, and peak time. But we could use that to figure out where we want these dominant poles. Let's now talk about that process, or what I will call, but now you've found how to produce a 2nd order equation that has k's sprinkled throughout, and we now need to figure out how do we find those k's. How do we find a value for k1, and how do we find a value for k sub 2? If I wanted to find a deadbeat controller, how would I adjust k1 and k2? If this is going to represent my closed, I thought I said on those phones. If I want to set this characteristic, this closed loop polynomial to give me a deadbeat response, what do I want to do? What do I want this to look like? Or where do I want my closed loop poles if it's a deadbeat response? I'm looking. You want them both at 0, right? You have 2, and you want them both at 0. I won't be giving you these hints on the final, so please, if somebody says deadbeat, you go, oh, I remember Tharp. What's that mean? Well, that means they're zeros. If I wanted zeros for my 2 poles, what do I want for these coefficients? What's scaling the z factor? 0. What's scaling the constant? 0. So you would really want this equation to just look like z squared. You would pick k1 and k2 to force those 2 coefficients to both be equal 0 at the same time. And that would be the feedback gain necessary to give you a deadbeat response. We probably won't always be doing a deadbeat response, so this designing of k is a more general approach. But do you see where we're going with this process? This is the process for finding k. We're not finding Nemo, we're finding k. Back to that terrible 2's, right? You just plug in Nemo. So if you're on the final, never mind. Let's let's go back to our example. We want to have a general approach for finding K1 and K2, or K3, K4 if we had more state variables. First, we want to decide on desired closed-loop poles. And what informs those desired closed-loop poles? Hearts, green clovers, no. Certainly, sir. We had a cereal commercial in here one day. Most of you missed it, but we were doing circles, hearts, and wedges, right? That informs the desired closed loop poles. In our example, maybe we decide, for whatever reason, that we want our desired poles to be at 0.8 plus j 0.2. Could you tell me if that's a stable set of poles on the final? Yes, you just have to square them and add them up, right? These are complex numbers. You take the real part squared plus the imaginary part. It's 0.64 plus 0.04. Yes, they're less than 1. So it is a stable set of poles. At least it's stable. And you could tell me then what would happen with its settling time, percent overshoot, and peak time for that choice, given those poles. Then, once we have this desired set of poles, we can create a desired characteristic polynomial with those poles. And maybe we'll call that delta sub desired of z. For our example, our desired characteristic polynomial would be then z minus 0.8 minus j 0.2 times z minus 0.8 plus j 0.2. Or, again, doing FOIL, we now have the first terms. What happens to the outer and inner? Because of the complex conjugate nature, those cancel. So we have minus j 0.2 times that z minus 0.8, and we have a plus j 0.2. So those go away, and we're left with a minus j squared. J is the square root of minus 1, so this now becomes plus 0.2 squared. That's where we could immediately, if somebody said, oh, I have closed loop poles at 0.8 plus and minus j 0.2, you could immediately write this down, this structure. And doing that, you now know you have z squared minus 1.6z plus 0.64 plus 0.04. Or our desired characteristic polynomial is now z squared minus 1.6z plus 0.68. That's our delta sub d of z. Step number 3 in this process is to simply equate the coefficients in delta sub d with those equation or the characteristic polynomial for delta sub k. So equate the coefficients in the two polynomials to find the unknown parameters or variables in k. Or we're now saying delta sub k of z is equal to delta sub D of Z. Meaning our delta sub K of Z from before was Z squared plus a minus 2 plus 3K sub 2 Z plus 3K1 minus 6K sub 2. And that now needs to equal delta sub D of Z, which was Z squared minus 1.6Z plus 0.68. And we would equate coefficients of like powers of Z. Maybe I'll do that after the fact and solve for K1 and K2. We have now two equations and two unknowns, K1 and K2. And we can now solve those for K1 and K2. Is that clear? How to do that? And that's how you now find find K in this process. And we'll pick up at that point next time.